A femtosecond is 1/4,000,000th of a second. When you compress a laser's energy into a pulse that short, the instantaneous peak power can exceed the entire electrical output of a nuclear power plant. The light simply vaporizes whatever it touches. We harness that extreme concentration of energy to remove material without transferring heat to the surrounding area. That thermal precision is what makes these lasers strictly necessary for industrial micromachining and delicate medical procedures, like laser eye surgery. Working with this technology can seem intimidating. We are going to demystify it by building and aligning one of these systems from scratch, a Ti-sapphire ring cavity laser on an optical bench. The required hardware is relatively straightforward. We need a pump laser, 4 cavity mirrors, a Ti-sapphire crystal, a low-power infrared alignment laser, and a standard piece of paper with a hole punched in it. Constructing an ultra-fast laser requires no magic. It relies entirely on understanding a few core physical principles and executing precise geometric alignment. Step 1 is understanding the physics. Inside a standard laser, longitudinal modes are uncoordinated frequencies, bouncing independently, chaotic, and out of phase. To create femtosecond pulses, we synchronize these modes into a locked phase relationship. Their peaks align in extreme constructive interference, collapsing into a single, intensely sharp, ultra-short pulse. For our specific build, we achieve this using Kerr lens mode locking. This relies on a specific property of our crystal. As highly intense light passes through it, the light physically alters the material's index of refraction. That localized change in the refractive index acts as an artificial lens inside the crystal itself. This temporary lens focuses and amplifies short, powerful pulses while actively suppressing weaker continuous waves. This self-focusing phenomenon happens spontaneously, but only if the physical optical layout on the table is perfectly tuned to support it. This schematic details our setup. An argon-ion pump laser injects a 500 nanometer beam upward through periscope mirrors into the ring cavity. This loop contains curved mirrors M1 and M2, flat mirror M3, and the M4 output coupler. In the middle, the Ti-sapphire crystal sits at a 30-degree angle. The spacing between these curved mirrors is critical. An initially collimated beam entering the first curved mirror must exit the second curved mirror completely parallel. Bolting these components to the table is only the rough draft. We now have to adjust their angles at the microscopic level, so the laser beam flawlessly retraces its exact path as it circles the ring. We start the precise alignment by turning the main pump laser off. Instead, we use a low-power 780 nanometer infrared diode laser. This allows us to safely work with the beam path without risking eye damage from the high-power pump. Our goal is to steer this IR beam through the M4 output mirror, send it through the entire ring cavity, and have it hit M4 again at the exact spot it entered. To verify this, we use the technique illustrated here. We place a paper with a 4 mm hole so the incoming beam passes through. If slightly misaligned, the returning beam won't make it back through the gap. It hits the solid border instead, creating a visible weak spot. To fix this, we start by making it worse. We intentionally misalign the M1 mirror on its vertical axis. This splits the beam, giving us 2 clearly visible spots on the paper to work with. Next, we adjust the M1 horizontal micrometer. We shift the 2 split spots left and right until they are perfectly aligned with each other horizontally. Then we move to the vertical adjustment. We slowly dial the M1 vertical micrometer, bringing the 2 spots closer and closer, until they physically touch, begin to merge, and perfectly overlap. By tracking the exact middle point of this vertical merge on the micrometer, we guarantee the returning laser beam retraces its path precisely on target. A piece of scrap paper has just given us sub-millimeter geometric precision. Ensuring the beam perfectly overlaps itself in the cavity is the physical prerequisite we need for mode locking to occur. With the geometry locked, we block the alignment beam and finally inject the high-power argon-ion pump laser into the cavity. To monitor our output, we place an optical power meter at the M4 exit point. We also attach an IR filter over the sensor to block the blinding green pump laser, isolating the infrared output of our crystal. Now we execute touch tuning. Do not turn any screws. Instead, apply slight physical pressure with a bare finger directly to the optical mounts. This microscopic mechanical pressure shifts the mirrors by fractions of a millimeter. You gently press the mounts until you find the exact position that registers a massive spike in infrared fluorescence on the power meter. When you locate that peak power, you carefully tighten the screws to lock the mounts in place. The geometrically perfect cavity, combined with the extreme intensity of the pump laser, allows the Kerr lens effect to take over, and the laser spontaneously mode locks into femtosecond pulses. Because we used a 780 nanometer diode for the initial alignment, the varying index of refraction in the sapphire crystal means our path is slightly off for our final 850 nanometer target wavelength. Minor micrometer tweaks will be required to optimize the final output. If you don't have the space or budget for a massive optical table and free space mirrors, you can build an all-fiber femtosecond laser. This alternative replaces the mirrors entirely with spliced fiber optics. You eliminate manual mirror alignment completely, but you trade it for the extremely delicate process of stripping and splicing fragile glass fibers. Once your TI Sapphire laser is mode-locked and stable, the next logical step is routing that beam into a chirped pulse amplifier. This will radically boost the energy of each pulse for advanced physics experiments. Whether you are adjusting free space mirrors by hand or splicing optical fibers, mastering cavity alignment and mode locking yields the exact same reward: the ability to harness the fastest, most powerful bursts of light ever created.